All right, ladies and gentlemen, the wishy-washy, handy-wavy stuff from the previous topic is over, and we go hardcore. So quantum control theory now, what we will need to do is firstly look through a lot of mathematical background, how quantum systems evolve, what are the mathematical properties of the evolution operators, how do we build them, what they are made of, and then we look at how to optimize quantum dynamics with respect to what the instrument can realistically do. So we will have a Hamiltonian. That Hamiltonian will come in parts that are not controllable, that are given to us, then parts that are controllable, like electromagnetic fields. And our mission is then to find such sequences of those fields as get the system from where it is to where we want it to be, subject to whatever constraints we have. So a lot of that is Lie algebras, and so what I need to introduce to you today is Lie groups and algebras. Now, interestingly, the chemists present know more group theory than the physicists because they had molecular quantum mechanics and, more importantly, crystallography. So for them, irreducible representations and group characters and so on is actually standard stuff. They've had it all. I think physicists had a bit less exposure to that because you have fewer useful symmetries in your undergraduate courses, but this time you're at about the same level, all of you present here. Okay, so item 1 on our agenda is groups, which we will now need to define and take a look at. So the first definition that I will give you is that of a semigroup, which is simply a set with a binary operation that is closed under that operation. So if we have some set G, so set G and some operation on it, which we'll simply call dots and usually just skip, then a semigroup is if you have two elements that live in G, so for any G and H that belong to G, their product under that binary operation still belongs to G. So G times H is in the same set. In other words, the set is closed under that operation, and that is called a semigroup. And there are plenty of examples, of course, from physics and chemistry. If you have some transformation of your vector space or some wave function space, or really whatever state space of the dynamical system is being transformed, then the two transformations applied sequentially is just another transformation, right? So the set is closed under the superposition, in this case, of the two operations, and then the dot would be the superposition. If you're dealing with rotations, then the dot would be a straight matrix product, right? Superposition of two rotation matrices. Then the superposition of two rotations is another rotation, and so again, the set is closed under the superposition. If additionally we have a few more properties, then the set is called a group. And for that to be called a group, we need two more things. Firstly, we need a unique identity element. So unique identity. So there should be an operator or an action or an object or whatever it is belonging to G, such that for any element that lives in G, its product with E is the same as G. So EG is the same as G. E is the same as G. So there is an element in the set that does nothing under this binary operation, and this is why it's called the identity element. And then the second thing is unique inverse for every element, every G. So we say that for every element G that lives in our set, there exists something that we can call G minus 1, the inverse, such that when we have G times G minus 1, it's the same as G minus 1 times G, and that's the same as doing nothing. And a good example here is rotations. As you know, in 3 dimensions, for every rotation, there is an inverse rotation, and if you apply the straight and then the inverse, you haven't changed anything. That's the identity operation, and so that one is a group, particularly since there is also a unit rotation that does nothing, right? The rotation by 0 angles. And so the rotation, the set of rotations of 3-dimensional space, is a group. Let us take a look at a few groups that you've had in your chemistry and physics. Of course, chemists would remember their simple geometric groups, right? For water, if you put a mirror plane in here and invert the molecule, you get the same molecule. If you rotate it around, you get the same molecule. This, the chemists know, is called the C2V point group. Of course, in crystallography then, if that water has crystallized and there's another copy of it next door, then there are additionally translations that leave the crystal invariant in any of the 3 spatial directions, and so that would become then whatever the crystallographic group is called for your particular crystalline modification of water, and there's a giant number of them at different pressures and temperatures. So we've had, as chemists, a detailed classification of these point groups, and then chemists were looking at their diffractograms in X-ray diffractometry as a function of that. And those of you who did physical chemistry remember your irreducible representations that lead to the molecular orbitals within Huckel theory. So these are the geometric point groups that chemists had. Physicists probably studied rotations quite a bit. So if we look at the set of all transformations of 3-dimensional space that leave the angles and the distances unchanged, the so-called orthogonal transformations, that group is called O3, the group of orthogonal transformations of 3-dimensional space. These are all rotations and inversions, because those leave the angles and the distances unchanged. If we leave the inversions out, if we say, okay, we would like to have a set of all specifically rotations that do not include inversions, so we will put them separately, like that, then the group of rotations is called SO3, special orthogonal group, and that is the group of all 3x3 rotation matrices with a unit determinant, which tells you that, okay, that particular rotation doesn't have an inversion component, and then the straight and the inverse coordinates are added via a product in here. So that is the rotation group, that's the inversion group, and the result is the group of all orthogonal transformations of 3-dimensional space. Those of you who did particle physics will vaguely remember these things cropping up in the standard model. Closer to the standard model, if we look at the transformations of a complex 2-dimensional space that leaves the norms and the inner products invariant, those of you who did spin will remember the U2, the set of all unitary transformations of a 2-level quantum system. And again, it is a product of SU2 and the inversion, where SU2 is a special unitary group, so that is the set of all unitary transformations of a 2-dimensional complex space, sans the inversion. And then you remember that these things have been describing spin, they will be describing isospin for the charge, and a few other things in quantum mechanics. Every time really you have a 2-level system, you have these toys. Okay, so that's chemistry, that's physics, and we need to take a closer look at the topology of these objects. Now, the first type that we can have are the groups that are finite and discrete. So firstly, of course, finite and infinite, That's simply the number of elements, right? If we look at the water molecule in isolation, well, it has the rotation, it has the reflection, it has the identity, and that's pretty much it. Well, there are two reflections, one like that and one like that, and then there's the C2 rotation. So there are just a few elements in there, and all other elements are their superposition. So that is a finite and discrete group. If you go into crystallography, of course, you can have translations by 1 click, by 2 clicks, by 3 clicks, and the crystals assumed to be infinite in crystallography, and so that group is infinite but countable. There are countably many elements in it, and it is still discrete. So the molecules are not translated continuously, they're translated in discrete jumps. If we look at these two, however, we will notice that these groups are continuous in that the elements on them are spaced densely. If we look at rotations, around every particular rotations infinitesimally close to it, there are other rotations. So if we set up a metric on this, so some kind of norm of g minus h, a measure of distance between two group elements in a matrix representation, it could just be the norm of the difference, or it could be the topographical distance on whatever manifold the thing's acting on. Anyway, if we have some kind of norm, then around every element g, we can draw an epsilon neighborhood, right, some radius in that norm. And if the group is finite and discrete, there will be a radius inside which there are no other elements of the group. They're all outside, right? So that is called a discrete group. However, if around a particular element in any epsilon neighborhood, however small, there are other elements of the same group, well, you remember the standard epsilon delta definition of a continuous function, right? Those of you who did serious big calculus courses, then that is a continuous group. And then additionally, so if continuous, parameterizable, so we have g as a function of some parameters, t1, t2, whatever it is, a continuous function of those parameters within some neighborhood and differentiable with respect to those parameters. So, and differentiable. Then the group is called a Lie group. And plainly, you can see that these two are Lie groups, SO3 and SU2, that they have parameters, for example, angles. In the case of SO3, you could parameterize it with, for example, 3 Euler angles, or the elements of a quaternion, or the elements of some rotation matrix. There are many parameterizations possible for rotations. And the rotation matrix is a continuous function of, for example, Euler angles. So there is a parameterization there. And it is clearly a differentiable one as well, so that is a Lie group. So in summary, right, what we have then is a set and a superposition, usually a binary operation, that is closed under that superposition, where there is a unique identity element that does nothing, and for every element there is a unique inverse that is called a group. If the group is additionally continuous, parameterizable, and differentiable, that is called a Lie group. And if you have n parameters there, it is called an n-parametric Lie group. In particular, SO3 is triparametric because you need 3 angles to describe an orientation of an object in 3-dimensional space. Now, obviously, the usual things apply to such definitions. A subset of G, which is itself a group, is called a subgroup. And if you look at SO3, for example, the group of all rotations, then C2V is a discrete subgroup of it, right? Because in order to rotate the water completely around, you need to apply a rotation, right? The elements of C2V are sitting discretely inside O3, but they are a subgroup of that particular Lie group. So Lie group in this case has a discrete and finite subgroup. Then the number of elements in the finite group is called the order of the group, and the number of parameters in a Lie group is called the dimension of the Lie group. Obviously, in this case, because there are infinitely many elements, the order would be infinite. Then one other important property that we need to consider, maybe I should use the lower board because we will be using this for something else. So group isomorphism. So groups G and H are isomorphic if there is a map that preserves the operation. So if there is a map, there exists a map from G to H such that for any G1 and G2 belonging to G, G1, G2, so the product of G1 and G2 that's been mapped over to H is the same as the product of the map of the first element and of the second element. That is to say, the images of the elements of G in H belong under that operation in exactly the same way as the pre-images had behaved in G. So the map conserves the properties of that binary operation. So an example of that would be two different rotation groups. If you simply look at your object from a different point of view, all of your matrices describing rotations will change, but of course that is substantially the same rotation group, and so you will have an isomorphism between the original and the transformed point of view. So that is, and the second thing that we need to take a look at is group direct product. Now that is somewhat an involved topic, but in a certain special cases, so direct product, and I will put it in bracket here, and I will not explain to you what that means. Those of you who do control theory in depth will sooner or later get there. So direct product of two normal subgroups of G. So if we have some subgroup 1, G1, product subgroup G2, that is a set of products of all of their elements. So GH such that G belongs to G1 and H belongs to G2. And this will come about when we are dealing with multi-spin systems, because the propagator groups for multi-particle systems will be related to the direct products of the propagator groups of the individual systems when we get there. Okay, so this is our definition of groups, and now we need to switch gears and define another object called an algebra, and then eventually we will establish the connection between algebras and groups. So completely separately, item 2 here, algebras. And an algebra is substantially a vector space, and you all know what a vector space is, on which additionally a multiplicative operation has been defined. So remember how you dealt with matrices, for example. Two matrices can be added together, they can be multiplied by a number, you can take linear combinations, and that's a space, right? It's a set with a multiplication by scalars and an addition operation that's closed under both operations. But you also remember that you could multiply matrices together, and that is not a part of the definition of a space. Then a space with a multiplicative operation defined is called an algebra. So going into the rigorous definition here. Okay, so a space, and we will call it small capital A over a field. So field is where numbers live, usually complex numbers in our case, is called an algebra if. And here come the properties. So if there is a binary product, so that takes two elements of A, so one element, another element, and so it maps two instances of A back into A. Right, so it is a binary product that takes an element of A, another element of A, and produces a third element of A. So the binary product with respect to which the space is closed. All right, so A is closed. So for any two elements, and you can think of them as matrices really, because you are physicists. There's no need to be unnecessarily abstract here. So for any two elements A and B that belong to that algebra, the product AB also belongs to that algebra. Right, so there is a closure. That product needs to be distributive on the left and on the right. So the next condition is distribution laws. On both left and right. So if we have A plus B product C, that's the same as A product C plus B product C. So if we have a linear combination here, it threads through. And if we have a linear combination on the other side, it also threads through. So A, B plus A, C. And a similar distribution law with respect to numbers. So all of that is for any A and B that live inside our algebra. And then additionally, for every alpha and beta that live inside the number field, so for any two numbers in here, we want the product alpha A, beta B to be the same as alpha, beta, AB. So we can take numbers out. Looks trivial, right, if you're already familiar with matrix arithmetic, but that is a part of the formal definition of an algebra. Now, so that is an algebra. Now, it is called a Lie algebra if there are two additional properties. So called Lie algebra after Sophus Lie, if additionally this product is antisymmetric, so A, B is minus BA, and there is an obscure identity, well, initially obscure, called Jacobi identity, that says that for any ABC, the commutator, well, this product is called the commutator in that case, A, B, C, plus B, C, A, plus C, A, B is 0. So if that holds and that holds, that is called a Lie algebra, and the product is called a Lie bracket, or in physics language, a commutator. And as you can see, the two things on that side and that side of the board are rather different, right? In an algebra, the inverse is not guaranteed to exist. the unit element is not guaranteed to exist with respect to the product. Of course, there is a unit element on metric spaces, right? It's the thing with norm 1, but needn't be on the product part of that. So it is our standard vector space with just some weird properties defined. So how is that related to this? Well, let's think about it. Let us go and define the exponential of a matrix, and then we will take a look at what that in practice means. Now, I will use a somewhat sloppy definition here of a matrix exponential because it makes use of a straight matrix product, right? Notice that only these brackets are defined, right? Technically speaking, we don't have a straight matrix product on this object, but let mathematicians worry about these technicalities. As you all remember, a matrix exponential is defined via the Taylor series. So n0 to infinity, a to the n over the n factorial. The definition of an operator exponential in general, because of course operator superpositions we can easily define, and then this series, its action on anything is thereby defined, and so we can have this matrix or operator or whatever really exponential defined like that. Let us take a look at the exponentials of the elements of this algebra. Remember Campbell-Baker-Hausdorff theorem, or rather you probably don't. I will simply tell you what that is. So CBH theorem. So here no proof, because we don't have the time in this module, but the exponential of a matrix A times the exponential of a matrix B is the following thing. It's the exponential of A plus B plus 1/2 commutator AB plus an infinite number of other terms which are all nested commutators. And therefore, this entity here is computable within our Lie algebra. Let us think about what that means. If we take an element A from that algebra, an element B from that algebra, because this is a commutator series, this element C that lives under the exponential, right, C, and this is e to the power C, is also an element of that same algebra. So turns out, if we have an algebra, the exponentials of its elements are a group in that sense for the following reason. Right, so we have closure, right, so E A, E B equals to e to the C, and if A and B belong to our algebra, then it follows from this definition and that Campbell-Baker-Hausdorff theorem that C is also the element of the same algebra. Then there is clearly a unit element in this thing, because e to the power 0, and the 0 does exist on the space, we can multiply any matrix by a 0, does nothing. Right, so if we have times A, if we work through that, B is 0, so we just have e to the A. So there is a unique unit element in the set of exponentials of all of these matrices. And then, of course, for every matrix there, we can easily prove, although that would take considerable amount of mathematics and doing in here, that although probably actually not. So if we have e to the a and e to the minus a, so b is equal to minus a, so that is going to be 0. That commutator is going to be 0, and all the other commutators are going to be 0. So that is actually e of 0, and that is a unit element. Well, let's call it just a unit here. So We have closure, we have a unique unit element, we have a unique inverse. Uniqueness takes a bit more time to prove. I will skip it, we don't have the time here. What is important is the fact that this, what's called exponential map, maps a Lie algebra into a Lie group. And let me run a little bit ahead and explain to you why this is very important in physics. Remember Schrödinger's equation solution. So we had d psi by dt was minus I h psi. And of course, all of you, having done even the minimal amount of physics now in this CDT, will remember that psi of t is e to the minus I h t psi of 0. The propagator was the exponential of the Hamiltonian. But then, of course, if we propagate it by a certain amount of time and then by a certain other amount of time, we would have the products of these two. The products of two propagators is another propagator. There's a closure. We can propagate the system backwards in time, so there's a unique inverse, right? And there's, of course, if we put time equals to 0, then there's the propagator that does nothing. So this set of all time propagators of quantum systems is, in fact, a Lie group. And from the fact that the Hamiltonians appear under the exponential, you realize that the set of all operators under which our molecular systems evolve, the spin operators for our spin systems and whatnot, are in fact a Lie algebra, and the people who did magnetic resonance have spent unknowingly a significant amount of time calculating all of these commutators. Right? Because they need to know the structure of this Lie group before they use it in practice. So you can see from this little detour outside that this is important because quantum mechanics in general and spin physics in particular has exactly this structure. Okay, so there's item 3 on our agenda here, exponential and tangent map. So the exponential map we have just covered, right? The exponential of a Lie algebra is a Lie group. Let us go backwards. Let us find out what is the relation between the group and the algebra, and can we go backwards? Well, let us take some element of our group. So we would say, okay, the group that is generated by our algebra will be a set of things that look like this. It will be an exponential of a general element of this algebra. And a general element of an algebra is a general element of a vector space. What is the general element of a vector space? It's a linear combination of basis elements. So we would pick up some basis and we would combine it with some coefficients. So alpha 1 v1 plus alpha 2 v2 plus and so on. Now, where all the alphas come from the number field, complex numbers in our case, more usually real numbers, in fact, for the kind of groups and algebras that we will encounter in physics. And then the set Vk is a basis of our set A, meaning that every element of A is a linear combination of these Vk's with some coefficients. So here, under the exponential, we have a generic element of A with, that is built by taking the basis elements with some numbers. Now, these are called generators of the group, and these are called parameters. And let me give you an example from just basic rotations. You will remember that if we look at a rotation operator on a three-dimensional space, so alpha, beta, gamma, for example, as a function of three Euler angles, then that was firstly the exponential of minus ILZ, where this is the Z angular momentum operator, a rotation around Z by gamma, followed by a rotation around Y by beta, followed by a rotation around Z by alpha, the so-called ZYZ convention for the Euler angles. And this is something that you would see in a lot of places, and a lot of people are rather unhappy with Leonhard Euler because he has the Z here twice. It creates quite a few inconveniences like gimbal lock in the dynamics of rotating systems, but you can see that, all right, looks pretty similar to this, and if we combine them using Campbell-Baker-Hausdorff theorem, then what this is going to be in general is the exponential of some coefficient a z Lz plus some coefficient a y Ly plus some coefficient ax Lx. So in general, this would be a combination of the three angular momentum operators with some coefficients, in this case complex coefficients, and this is how a generic rotation operation looks like. So the angular momentum operators are rotation generators and the angles are rotation parameters, and that is a particular instance. In fact, this is the SO3, right? The rotation triparametric group of rotations. So that is the exponential map. We take an element of our algebra, we exponentiate it, and we obtain the corresponding element of the group. The propagator group here, incidentally, is uniparametric because you only have one time, and the algebra of the Hamiltonians is the subject of giant books called quantum mechanics, right? This is what determines the energy that pushes us forward through time. Now, let us try and recover one of these generators out of the group element. So clearly in this case, G depends on alpha 1, alpha 2, and so on. So actually, if we look at it, G is a function of alpha 1, alpha 2, and so on. And as befits really the Lie group, right? Continuous, parameterizable, and differentiable, because the exponential is all three. Let us take a derivative of this at the origin. So let us take, for example, that dg by d alpha k at the point where alpha 1 is alpha 2 and so on is equal to 0. So just the tangent coefficient at the origin. What this is going to be is, well, let's think about it. Let's take that exponential at that point. So by definition, this is a limit of alpha k going to 0 of this at that point with alpha k incremented. So we will have the exponential of, all of them are 0 except for the alpha k, which we have incremented, so alpha k vk minus the original value of g at the 0 point, which is the exponential of 0, divided by alpha k, the standard limit definition of the derivative. Well, you all remember how to truncate Taylor series. Let's truncate it to second order. So we are going to have a limit alpha k going to 0 of, in this case, unit operator minus alpha k vk plus elements of the order alpha k squared minus, this is clearly the unit operator, divided by alpha k. Well, if we look here, the unit is going to cancel, alpha k is going to cancel, and this will go to 0 when we take the limit. So that, in fact, it should be a plus, is equal to vk. So that is how we recover the generators of the algebra if we know the element of the group. We differentiate it with respect to some parameter at the origin, and we obtain the generator of the group with respect to that parameter. If you look then at what this is, these are the basis elements of the space that underpins our algebra. So this is a tangent space at the origin. So we may have some complicated manifold that describes our group. It could be something really quite horrible and topologically hard to work with, something, some kind of manifold. And then if we pick ourselves the origin somewhere here, and we draw a tangent space at that origin, like that, a tangent plane in this case, then however complicated the manifold is, so this is our G, the group, the algebra that's generating that group has the structure of a vector space generated by these derivatives, and the map from A into G is the exponential, and the map from G to A back is the tangent alpha k. And that is the relationship that we needed to explore today. So, summary, this is something that the physicists and the chemists present have already seen in different disguises throughout your undergraduate programs, and all of that really is inspired by and required by this, right? That the set of all time propagators for a time evolving quantum system is a Lie group, and then the set of generators of forward time evolution is therefore a Lie algebra, and we will spend a considerable amount of time studying those things because we need to design these propagators within the optimal control theory. So the definition of a group starts with a semigroup, which is just a set with a binary operation that is closed under that operation. If we additionally require a unique element that does nothing and a unique inverse for every element, then that is called a group. Groups can be discrete and finite, like a single water molecule, discrete and infinite, like the symmetries of a water crystal, or they can be infinite and continuous, and if there is a parameterization and the group element is differentiable with respect to those parameters within some neighborhood, then in that neighborhood that is called a Lie group. Separately, we can define a space of some operators, in our case in physics, over typically a field of complex numbers, so this is normally C, and a vector space is just a bunch of linear combinations. And we can additionally define a binary product there, which is really inspired by the commutator from quantum physics. And if the set is closed under that commutator, the commutator has the usual distribution laws with respect to the operators and the scalars. If it's additionally anti-symmetric and Jacobi identity holds, then this is called a Lie algebra. And the reason why Lie groups and Lie algebras share Sophus Lie's name is that if we look at the exponentials of the elements of a Lie algebra, the set of those exponentials turns out to be a Lie group, and I've sketched you a proof for that. Now, that defines the map from the algebra to the group, that's the exponential map. We can define the map back from the group to the algebra, and that's called a tangent map. So the generator of the group with respect to some parameter is the partial derivative of that group element with respect to that parameter at the origin. And the origin corresponds to the 0 point of the Lie algebra and the unit operator of the Lie group, because the exponential of a 0 is 1. And so this is called tangent space at identity. It has a structure of a vector space, and this is how you obtain it. All right, all of that will take a considerable amount of time to shake in your heads, but all of you kind of realize that this is all familiar stuff in a different disguise, right? So you will eventually get used to it. Okay, that's all I had to say.